Okay, this vodcast is going to be on the acid-base properties of salts. So basically, it's about how salts can affect the pH of a solution. So, as a refresher course, salts is another name for ionic compounds. So, salts consist of both a metal and a nonmetal. And salts can produce neutral, basic, or acid solutions depending on the ions present. So, you have to pay attention to which ions are present. Okay, let me stress that you have to make sure you remember your strong acids and strong bases. It's important that you know which ones are which because they play a part in these identifying salts and how it'll affect pH. So some of the easiest, and there's two different type of ways that salts can affect pH. There are neutral solutions, acidic solutions, and basic solutions. And we'll begin with the easiest, which is going to be neutral solutions. So conjugate bases of strong acids has no affinity for protons. So these are conjugate bases of strong acids, HCl, and so just some examples how HCl would be a strong acid, and HNO3, two of the ones you should have memorized. So conjugate bases of strong acids have no affinity for protons. So you throw this in solution, they break apart, you're just going to get close to 100% H ions and chlorine ions and 100% H ions and nitrate ions in solution. Cation ions from strong bases have no affinity for H ions, nor do they produce H ions. So something to the effect of NaOH would be an example, or KOH. These are very strong bases. Oops. Click very well. So KOH, these are very strong bases, and these ions, cation ions, do not attract anything. They are basically loner ions in solution. They do nothing. So when you mix the two, a conjugate base of a strong acid with the cations from a strong base, you have a salt that does not contribute to pH, and this is important. Does not contribute to the pH of a solution. Therefore, salts that consist of the cations of strong bases and the anions of strong acids have no effect on pH. So perfect examples: NaCl, KCl, NaNO3. You put this in a solution of water, you measure the pH is going to be a 7 from where these pieces are coming from. So it's important to know where each of these pieces come from, and you'll be able to determine what the pH is. In this case, it's a really quick answer, pH of 7. Okay, for this one, we're going to see how we can produce basic solutions. So salts that produce basic solutions, basically the conjugate base of weak acids have affinity for protons. So here we have the acetate ion and the cyanide ion, and really these really come from like a weak acid. So C2H3O2. So this is acetic acid, which is a weak acid. This is my conjugate base, and this does attract hydrogen ions. So if the anion of a salt is the conjugate base of a weak acid, it'll form a basic solution. So if the anion of a salt, so this anion of a salt is a conjugate base of a weak acid, it'll be basic in solution. Therefore, base reacts with water to produce a hydroxide ion and conjugate acid. Okay, and before I go on with an example, here's a special relationship we have here you should be aware of. At this point, you should know equilibrium expressions for acids and equilibrium expressions for bases. When you multiply the two together, you're going to get Kw. And remember that Kw equals 1.0 times 10 to the negative 14. So that can come in useful a little later. So please remember that. So let's do this by example. It's probably the best way to tackle this. Okay, for this example, they want us to find the pH of a 0.30 molarity of NaF solution. And they give us the Ka value for HF, which is 7.2 times 10 to the minus 4. So why would they give you a Ka value for HF when you're dealing with NaF? You'll see why this is kind of important. So one of the first things you should take a note is you have an NAF. Na comes from basically a strong base. So NaOH just as an example of where this strong base could come from. The F comes from basically a weak acid, HF. So what I did was I split both these apart and added an H and an OH to each to see where they both come from. So this is definitely conjugate base from a weak acid. Okay. So the way we're going to do this is the Na is not going to do anything in solution. It's just a loner ion. It remains by itself in solution, so it's nothing. But now you have this free fluorine ion in solution. And don't forget, this does break apart in solution. It's just the Na does nothing, but the fluorine will. So the first thing we have to do is write a balanced equation for this. And the way I'm going to write this is you have fluorine ion, and do not forget that water is present in the solution. And I'm going to write water as HOH just to keep it so you can see where this is happening here. So the fluorine is actually going to take the H from water, and we're going to produce HF plus, well, now you have a single hydroxide ion floating in solution. So this is an example of a salt that produces a basic solution because it's making hydroxide ions in solution. So a basic salt. At this point, after you have your balanced equation, you're going to ice it. So icing is something you should be familiar with. So initial change equilibrium. The initial amount of fluorine is 0.30. Water does not play a part in here at all because it's a liquid. My initial amount of this will be 0, and my initial amount of that will be 0. This is going to be minus x, nothing here, a plus x, a plus x. This is going to be 0.3 minus x. Now we're at the equilibrium part, again nothing, a plus x and a plus x. Okay, now to write the expression. This is producing hydroxide ions, but they gave me a Ka for HF. So at this point I cannot use Ka because I'm not producing hydrogen ions. I'm going to use this nice relationship that I showed in the previous slide. Ka times Kb equals Kw. And I need to find Kb for this. And we need to use Kb because we're producing hydroxide ions in solution, not H ions. So I'm simply just going to divide both sides by Ka, and I'm going to get Kb to equal this expression. Kw should always be known. So 1.0 times 10 to the minus 14 divided by the Ka value, which is 7.2 times 10 to the negative 4. Okay, so I'm going to plug this in and I'm going to solve, and I'm going to get Kb to be 1.4 times 10 to negative 11. So I'll plug this in my calculator and this is what I got. Now that I have my Kb, I can finally set up my equilibrium expression. So 1.4 times 10 to the negative 11 equals x squared over 0.3 minus x. Okay, at this point you should be familiar with how to do these, and I'm going to assume that 0.3 minus x is equivalent to, okay, we're not printing here, there we go, 0.3. So what I'm really going to get is x squared over 0.3 only. Okay, to speed up this process, I'm going to plug this in the calculator. Okay, and in my calculator, I'm going to get x to equal 2.0 times 10 to the minus 6. Once you make an assumption, you have to check 5% rule. So I'm going to check 2.0 times 10 to the minus 6 divided by my initial amount, which was 0.3 times 100. And again, let me plug this in my calculator. And I get a super, super, super small number, percentage. So, oops, I get a very small number, 0.0006. Well, I'm not even going to write it. It's definitely passes the 5% rule. So now that I have my x, and my x is this, I can now calculate pH. But again, they're looking for pH, and I can't calculate pH from hydroxide, so I'm going to use the other way. POH equals negative log of x, and I'm going to plug this in my calculator, and we get 5.69 is my POH. But remember, I have to subtract it from 14 because I want pH. So 14 minus 5.69, and I'm going to get 8.31 is my answer. Okay, so it makes sense. We have a salt that can form a base, and the solution should definitely be above 7. And at this point, it is 8.31, and it makes sense to what type of solution this should be.